Hey guys, today we're going to learn about the relationship between continuity and differentiability. Now the word differentiability means the ability to find the derivative of a function, to know that you'll have a derivative once you take your function, do the work, and then plug in a number, it actually equals to a real number. So in this lesson, we're going to see if we can answer the following questions. If a function is continuous at a particular value of x, does that imply that it is also differentiable? Or if a function is differentiable, does that mean that it must be continuous? So let's investigate. Looking at this graph, we have f of x is equal to the square root of x squared minus 4. For our first question, it says, based on the graph, is f of x continuous at x is equal to 2? And explain your reasoning. In order to determine if a function is continuous, we have to go through the three-part definition of continuity. To review, the first part of continuity is to find the function value. So I'm going to find f of 2 and make sure that f of 2 exists. When I look at my graph, f of 2 is equal to 0. So my function value does exist. The second part of continuity is to find the limit. So we're looking for the limit as x approaches 2 of f of x and make sure that this limit exists. In this case, here's 2. We have the right-sided limit, but there is no left side. And remember, in order for a general limit to exist, the right must equal to the left. So this limit does not exist. At this point, I can determine that my function is not continuous at x is equal to 2. But just to review, that third part of continuity is going to be that the function value must equal to the limit value. So we would say here that f of x is not continuous at x is equal to 2 because, first of all, because the limit does not exist. So we would say because the limit as x approaches 2 of f of x does not exist. Now we're going to see, just because it's not continuous, maybe it is differentiable at x is equal to 2. So we're going to see if we can find the value of f prime of 2. So this is my f of x, which I would have to rewrite as x squared minus 4 raised to the 1/2, so that I could find the derivative. F prime of x is going to be, I have to use a chain rule, 1/2 x squared minus 4 raised to the negative 1/2 times the derivative of the inside, which is 2x. Now let's clean this up. This 1/2 and the 2 would end up canceling. And everything here is going to move down to the denominator because of that negative exponent. So my f prime of x is going to be, we have this x here, that's going to stay in the numerator, over, this is negative exponent, and it's 1/2, so that's the square root of x squared minus 4. Now let's plug in f prime of 2. When I plug in 2, I get 2 over the square root of 2 squared, which is 4, minus 4. What this ends up giving me is 2 over 4 minus 4, which is 0, and the square root of 0 is 0. This value here is undefined because we have 0 in the denominator. Therefore, f of x is not differentiable. At x is equal to 2. So it would be differentiable if I got a real number, but since I got that it's an undefined value, then it's not differentiable. Let's look at a couple more graphs. Here we have f of x is equal to x raised to the 2/3 plus 2. Based on the graph, is f of x continuous at x is equal to 0? So let's go through my three-part definition. F of 0, when I look at f of 0, my f of 0 is 2, so my function value exists. Now let's find the limit value. The limit as x approaches 0 of f of x is going to also equal to 2 because the left side equals to the right side. So since these two things are equal, that means that the graph of f of x is continuous at x is equal to 0 because, and the reasoning would be f of 0 equals to the limit as x approaches 0 of f of x. Now let's see if we can take that derivative, plug in 0, and see if we get a number. If we get a number, then it would be differentiable at x is equal to 0. So f prime of x, using the power rule, is going to be 2/3 x. I'm going to subtract 1 from the exponent. So I'm going to subtract 3 over 3. That would give me negative 1/3. And the derivative of 2 is 0. So this is equal to 2 over 3 cube root of x. Now let's plug in 0. So f prime of 0 is going to equal to 2 over 3 times the cube root of 0, which is 0, which gives me 2 over 0. Again, we end up with undefined. So this means that f of x is not differentiable at x is equal to 0. Now let's look at this graph. Based on the graph, is g of x continuous at x is equal to 1? And explain your reasoning. So at 1 is right here. We're going to do g of 1. Now I can use the graph, but it looks like it's not an exact value, so I'm just going to plug it into the function. So this would be 3 over 1 plus 1, which is 2. So this is my defined value. Now let's do the limit value. The limit as x approaches 1 of g of x. If we look at the graph, we can tell it's continuous. It does connect. The limit from the left is going to equal to the limit from the right, which is also going to be 3 over 2. So this means that f of x is continuous at x is equal to 1 because f of 1, g of 1, this is g. G of 1 is going to equal to the limit as x approaches 1 of g of x. Now let's see if I could take that derivative, plug in 1, to determine if it's differentiable. In order to find this derivative, you can use the quotient rule, or you can rewrite this as 3x plus 1 to the negative 1. Since I can bring up that entire denominator, and since the numerator is just a coefficient, I would use the chain rule here. Up to you. You can use the quotient rule or the chain rule. It's going to give you the same answer. I think this way is a little bit less of a hassle, so I'm going to use the chain rule. So g prime of x is going to equal to, the negative 1 gets multiplied with the 3, so negative 3, x plus 1, subtract 1 from the exponent, which is negative 2, times the derivative of the inside, which is just 1. So g prime of x is equal to negative 3. This is a negative exponent, so I'm going to move it down to the denominator, x plus 1 squared. Now I'm going to plug in 1. So g prime of 1 is going to equal to negative 3 over 1 plus 1 squared. 1 plus 1 is 2, and 2 squared is 4. So since I get a real number, that means that g of x is differentiable at x is equal to 1, because we got that g prime of 1 is negative 3 over 4. So what determines differentiability? How come we were able to find derivatives of some and not of others? In order for a function to be considered differentiable, it must meet two conditions. One, the function must be continuous and have no cusp. A cusp is a sharp point. So like if you have a graph that does this and then all of a sudden it goes like that, you see how this is a sharp point. So that would be a cusp. So functions are not differentiable at points where it would be not continuous and where you have a cusp. And the other condition is that the limits, these limits here must be true. And that is the limit from the left of that value of the derivative must equal to the limit of the right of that derivative. So based on these graphs here, let's determine whether these graphs would be differentiable at x is equal to 0. Here, at x is equal to 0, we have an asymptote. That means that the function is not continuous. So no, this graph would not be differentiable at x is equal to 0. Here we have a parabola, and this is x is equal to 0. This function is both continuous and does not have a cusp, so yes, this would be differentiable. On this graph, this is the absolute value, and you can see here at 0 we have a sharp point. This is my cusp, and functions are not differentiable when you have a cusp, so this function would not be continuous. Now we're going to see how to determine if a function is continuous and differentiable if we're given a piecewise function. Remember that a piecewise function means that your function is made up of pieces. So for the first part here, we have the square root of x plus 1 for when x is between 0 and 3, and then 5 minus x for when x is between 3 and 5. So first, we want to determine, is the function continuous at x is equal to 3? So for continuity, remember those three parts. I first need my function value, g of 3. 3 is defined for this top function. Since that, you see here the inequality, you have the equal sign, so x equals 3 here. So I'm going to plug that in there. The square root of 3 plus 1 is the square root of 4, which is 2. So that's my function value. Now I need to determine the limit value. Now remember that the limit from the left must equal to the limit from the right in order for the general limit to exist. Here, this is the number we're looking at, the 3. This is for when x is less than or equal to 3. So this is the left side of 3, which I've already evaluated. This is also equal to the limit as x approaches 3 from the left of g of x. Now I need to make sure that the limit from the right, see this is for when x is greater than 3, is also equal to this value. So we're going to find we're going to find the limit as x approaches 3 from the right of g of x. We plug that in, we get 5 minus 3, which is 2. So this is my left limit, this is my right limit. That means that the general limit as x approaches 3 of g of x does exist, and it equals to 2. Since all of these values equal 2, this would imply that g of x is continuous at x is equal to 3 because g of 3 equals to the limit as x approaches 3 of g of x. Now we're going to see if g of x is differentiable when x is equal to 3. To figure out if it's differentiable, we have to set the derivative from the left equal to the derivative from the right. So we got to use limits. So we're going to do the limit as x approaches 3 from the left of g prime of x, and make it equal to the limit as x approaches 3 from the right of g prime of x. So for the left side, we need to find the derivative of the square root of x plus 1, which is x plus 1 raised to the 1/2. The derivative of that would be the chain rule, so 1/2 x plus 1 raised to the negative 1/2 times the derivative of the inside, which is just 1. And we make that equal to the derivative of the right. And the derivative of 5 minus x is negative 1. So now let's rewrite this. This is 1 over 2 square root of x plus 1. Since again, negative exponent means that the x plus 1 is going to go down to the denominator. And since the exponent is a fraction of 1/2, that is the square root. So it goes down with the 2, since I already have a 2 in the denominator. And now I'm going to make that equal to 1. Now we made our limits here. This is the limit as x approaches 3. So what I'm going to do now is I'm going to plug in 3 for the x. So this is going to be 1 over 2. 3 plus 1, which is 4, is equal to 1. And we want to check if these are equal. If they are equal, then this function is differentiable. If it's not equal, then it's not differentiable. 1 over 2 times the square root of 4 is 1 over 2 times 2, which is 4. And 1 over 4 does not equal to 1. So this means that g of x is not differentiable at x is equal to 3. Now let's see what happens when I want to figure out what variables would make my function both continuous and differentiable. Here we have for what value of k and m will the function below be both continuous and differentiable at x is equal to 3. For our function, we have h of x is equal to k square root of x plus 1, where x is between 0 and 3, and mx plus 2 for when x is between 3 and 5. So first, we want to make sure that the function is going to be both continuous and differentiable at x is equal to 3. So our first step is to determine if the function is even defined at that value. I look here, this is 3, I see that it equals 2, so it is defined, so I can move forward. First, we're going to set up our continuity. We want to make sure that these are going to be equal. In order for those to be equal, I'm going to set up my limits. We always use limits to figure these parts out. So I'm going to do the limit as x approaches 3 from the left of h of x has to equal the limit as x approaches 3 from the right of h of x. I don't have to find h of 3 because h of 3 is also the limit from the left of h of x. So they are the same thing. So as long as these two parts here are equal, then that means that the defined value is going to equal to the limit value. So now, once I've set up my limits, again, knowing that this is the left and this is the right, I'm going to make these equations equal to each other. So k times the square root of x plus 1 is equal to mx plus 2. Now these limits, we're making them equal for when x is 3. So now I'm going to plug in 3. So this is going to be k square root of 3 plus 1, which is 4, is equal to 3 times m plus 2. The square root of 4 is 2, so the equation I get is 2k equals 3m plus 2. So I have done my step 2. I set the left side of the function equal to the right. I plugged in the x value, and now we are left with an equation in terms of these variables. I have 2k equals 3m plus 2. I can't solve for k and m with just one equation. That means I'm going to need a second equation. And I get that second equation by setting the limits now as x approaches the same value, 3. But remember, we're making this both continuous and differentiable. So what's in blue here, this is for continuity. What's in red, this is for differentiability. So that means that I'm finding the limits for when h prime of x, as x approaches 3 from the left, is equal to the limit as x approaches 3 from the right of h prime. So now that means I have to find the derivatives of each individual part. Now k and m are not variables. They are numbers. I just don't know what those numbers are yet. That's what I'm trying to figure out. But we're going to treat them as coefficients. So the k and the m just tag along with those derivatives. This top part, this is k times x plus 1 to the 1/2. So when I find that derivative, I got to use the chain rule. I'm going to use the 1/2 to the front, k, times m plus 1, now raised to the negative 1/2 because I subtract 1. Oops, I put m here. Sorry, that's k, x. Times the derivative of x plus 1, which is 1. And that's going to equal to the derivative of the right side. Remember that m is a coefficient. M times x, the derivative would be m. And the derivative of 2 is 0. Now remember, these are my limits for when x is approaching 3. So now I'm going to plug in x is equal to 3. So, sorry, before I do that, let's rewrite this part here. This x plus 1 to the negative 1/2 is going to go down to the denominator with the 2. So I have k is going to stay in the numerator over 2 times the square root of x plus 1. Now let's plug in the 3. So I get k over 2 times the square root of 4 is equal to m, which this gives me k over 2 times the square root of 4, which is 2. So 2 times 2, 4, is equal to m. So now what I have is a second equation. From here, okay, so let's see where we are here on our steps. We found the derivative of the left and make it equal to the derivative of the right. We plugged in the x value and we are left with another equation in terms of those variables. Now those two equations become our system, and we have to now solve that system. So here's one equation, and here's the other. So I got 2k is equal to 3m plus 2, and k over 4 is equal to m. You can use whichever method you'd like. Here I see that m is already solved for. So I'm going to go ahead and use substitution because I can plug in that k over 4 as m in the other equation. So this is going to become 2k is equal to 3 times m, which my m is k over 4, plus 2. If I distribute that 3, I get 2k is equal to 3k over 4 plus 2. If we ever want to cancel a denominator, just like here, I don't want to work with fractions, we can take the entire equation and multiply it by whatever is in the denominator, which in this case is 4. So I'm going to distribute this 4 so that way I don't have to worry about any more fractions. And that would give me 8k is equal to 3k over 4 times 4 is 3k plus 2. Now I can solve for k. Subtract the 3k. We get 5k is equal to 2, and then divide the 5. So k is equal to 2 over 5. So I got k. Now I need m, which this is my equation here for m. So I'm going to plug it in there. M is going to equal to 2 over 5 over 4, which this is 4 over 1. So now I can copy, change, and flip since I'm dividing fractions. So 2 over 5 times 1 over 4, and that gives me 2 over 20, which can be simplified to 1 over 10. So this would be my value for m. Let's try one more using this process. We want to find here the values of a and b, where the function will be both continuous and differentiable at x is equal to 1. Okay, so first we need to determine continuity. If this function is going to be continuous, the function value must be defined, which you see that equal to symbol, it is defined. So now I'm going to set up my limits. The limit as x approaches 1 from the left of f of x must equal the limit as x approaches 1 from the right of f of x. Now we're going to replace these limits with those equations. So 3ax squared plus 2bx plus 1 must equal to ax to the fourth minus 4bx squared minus 3x. Because my limits are for when x is 1, and again, I get that 1 because that's what we're evaluating for, we're going to plug in x is equal to 1. So since x is 1, then 1 raised to any exponent is going to be 1, so 1 times whatever is next to it is just going to be itself. So this is 3a plus 2b plus 1 is going to equal to a times 1, so a, minus 4b minus 3. So at this point, this is my equation, but knowing in advance that we're going to end up with a system, I am going to move the a's and b's on one side and the constants on the other. So I'm going to subtract this a here, move it there. I'm going to add this 4b. Oops, I wrote it backwards. And then I'm going to subtract this 1. So that way my constants are on the right and my variables are on the left. And this gives me the equation 2a plus 6b is equal to negative 4. Okay, so that is for continuity. Now let's do differentiability. In order for my function to be differentiable, the limit as x approaches that same value, so 1 from the left, of f prime of x must equal the limit as x approaches 1 from the right of f prime of x. Looking at my functions here, to find the derivative, we're going to apply the power rule. And when we apply the power rule, remember that a and b are part of the coefficients. So 2 gets multiplied with the 3a, so that's 6a x plus 2b is my coefficient, so b plus 2b. And then the derivative of 1 is 0. So that's that. Equals, now down here, my derivative is going to be 4ax to the third minus 8bx minus 3. Once I found my derivative, I'm going to go ahead and plug in the x value of 1. So 6a times 1 is 6a plus 2b is equal to 4a times 1 minus 8b times 1 minus 3. I'm going to move my a's and b's over, so minus 4a over to the left plus 8b over to the left. And I have no coefficient or no constants here, so we just have the negative 3. So this equation is going to be 2a plus 10b is equal to negative 3. I am now ready to set up my system. I have this equation and this equation. So I'm going to go ahead and stack them. 2a plus 6b is equal to negative 4, and 2a plus 10b is equal to negative 3. For this system, I'm going to use the elimination method because I noticed that for my a's, it would be easy to eliminate if at least one of them was negative. So I'm going to multiply this bottom one here by negative 1. So this top equation is not going to change. 2a plus 6b is equal to negative 4. But the bottom equation is going to be negative 2a minus 10b is equal to positive 3. My a's here would cancel. 6b minus 10b is going to be negative 4b, is equal to negative 4 plus 3, which is negative 1. Divide by negative 4, and we get that b is equal to 1/4. So I got my b. Now I need a. In order to get a, you can plug in b into either of the original equations. I'm going to plug it into the top one. So 2a plus 6 times b, which is 1/4, equals negative 4. This will give me 2a plus 6/4 is equal to negative 4. I don't really want to work with this fraction, so I'm going to multiply the entire equation by 4, so it cancels out with that denominator. So I'm going to distribute the 4. 4 times 2a is 8a, plus 6/4 times 4 is 6, is equal to 4 times negative 4 is negative 16. Subtract the 6, we get 8a is equal to negative 22, and then divide the 8. And we get that a is equal to negative 22/8, which then a can be simplified to negative 11/4. And that's continuity and differentiability.